All right, so we have a short lecture today, and even though it's short, I think the topic is extremely important, so we need to discuss a little bit about what's called the exponential family of distributions. We have seen most of these distributions today, but obviously we're going to try to generalize the notation and some of the outcomes. All right, so not surprising, in this exponential family we will discuss today, there is a huge number of distributions, the Bernoulli, the beta, the binomial, the Dirichlet, the gamma, the Gaussian, etc. But there are some distributions that they are not in this family. So things like the student t distribution, the Laplace distribution, a mixture of Gaussians. The nice thing is, all of these distributions can be treated in a very unifying way, okay, at the cost of some more complex notation, but somehow the results that we will see that are true for the exponential family can be applied to any of these distributions without having to do any proofs. So exponential family of distributions is used because it makes the algebra very simple, okay, and it is very important. All right, so let's get things started with notation, okay? So we define, so we have a distribution over X, and we have parameters that we define here as eta, and this is how the distribution looks like. Some function of X, some function of the parameter theta, and then exponential of eta transpose u, okay? So you can see why this is called exponential family because of this term. Exponential of eta transpose u. U is some function of X that you can extrapolate from what we have done up to now. It's really the sufficient statistics for the distribution, okay? So for example, you can imagine in a Gaussian, u of X is going to involve X and X squared, okay? So generally speaking, u is a vector, all right? And eta is a vector. You can rewrite this distribution with a new definition, so you can put the g of eta inside by defining a of eta to be minus log of g, and another very familiar form of the distribution is h of x times exponential eta transpose u minus a of eta. The distribution is normalized, and actually this factor g of eta that you see here is actually the factor that enforces the normalization. So when you take the integral of this in x, you get g of eta can go outside, it's not a function of x. So this thing is equal to 1, okay? And a lot of times, because we like to denote distributions with a normalization factor in the denominator, so you can see that the normalization factor here is really 1 over g. All right, it's 1 over g, and if you use this definition of a being minus log of g, you can see minus log of g gives you log of the normalization factor, okay? And so a of e is log of this complicated integral in x, okay? And I know for now you may look at it and you say, wow, what is that? But almost in every part of physics, chemistry, I am assuming biology, everything else, this is very much related with free energy, okay? And that's why calculations that involve the partition function are very complicated, because you have the log of an integral over a very high dimensional space x. So again, I will put this formula up in every slide so you can get familiar with it. So any distribution that has the form of a function of x, exponential of eta transpose u, divided by this normalization factor z, is an exponential in the exponential family of distributions. So these parameters are called the canonical parameters of the distribution, okay? We haven't really seen this parameterization yet, right? I remind you, like, you know, if you think of a Gaussian, the parameterization that we have seen is in terms of the mean, the variance, and things like that. These are different type of parameters that we call them natural parameters. Now, what relations they have with the mean and the variance is going to come up as a miracle at the end of the day, but there are new parameters, okay? So this is a completely different parameterization, okay? Here, you know, I denote that these parameters theta are parameters of some other parameters theta that, you know, related to the distribution. So I'm writing this as eta of theta, okay? And we will see through these various examples what eta is and what theta is. So again, remember that the definition of A is minus log of g. All right, so let's do some examples to see why some distributions are in the exponential family. So we're concentrating on the Bernoulli distribution. This is the coin tossing experiment. Mu is the probability of heads. So x is a binary variable. 1 is heads, 0 is tails. So the probability of x given mu is mu to the power x, 1 minus mu, 1 minus x, right? So to put this in the exponential family, so this form here involves mu, which is actually the mean of this distribution. So this is not the parameterization we're interested in. So we want to make this to look like an exponential distribution. So we write this as this nice exponential. Look at it and tell me that you agree that it's okay. I mean, really, this is log of mu to the x, right? And log of 1 minus mu to 1 minus x. And the log of this is really the log of the product. And x and log cancel and gives you this, right? All right? So I'm getting this. And then I'm going to rewrite this as there is this term 1 log of 1 minus mu. An exponential of the log, it will give me 1 minus mu, and then I have exponential of the log of mu divided by 1 log of 1 minus mu times x. All right? So this is immediately in the exponential family. You can see immediately the parameter theta is this log of mu divided by 1 minus mu. So somehow you can see immediately there is a direct relation between mu and eta. And it comes in this case, the relation is defined by a sigmoid function. Interesting, okay? Because we will see sigmoid functions being used in machine learning all the time. So it comes that mu is the sigmoid of eta, okay? And there's no function h of x on the front, so this is g of eta. So g of eta is 1 minus mu. If you plug in this as a function of eta, g of eta comes to be the sigmoid of minus eta. You can prove actually this, right? If you put eta and minus eta, 1 minus sigma calculated eta is sigma minus eta. So again, this is eta, this is g of eta. You can invert this relation. This will have significance. We will see today. So the distribution is really written like that. The sufficient statistics u is really nothing else but x. Okay, h of x, there's nothing in front, is 1. And this partition function, which is minus the log of g, if you write it explicitly, is log of 1 plus e to the power eta. Okay, so these parameters are called the canonical parameters of this Bernoulli distribution. So the Bernoulli distribution fits on this general form of the exponential family. All right, if you take the beta distribution, you have a normalization factor, a constant, and then you have mu to a minus 1, 1 minus mu beta minus 1. Again, you write this as exponential of this two weighted sums of logs, and immediately you can see that the sufficient statistics here, this is a distribution in mu, so the sufficient statistics is log of mu and log of 1 minus mu, okay? You remember before the variable was x. When you write the beta distribution, the variable here is mu. So the sufficient statistics is log of mu and log of 1 minus mu. The natural parameters is a minus 1 and beta minus 1. The coefficient h, there's nothing on the front, is 1. And the normalization factor g is this ratio of the gamma functions. And the partition function is log of this. Okay? So the beta distribution fits in the exponential family as well. If we make the algebra a little bit more interesting, and you may think unnecessarily very complicated, okay, would be to play with a Gaussian. So if you expand the square, you get an x squared, a mu squared, and x. So the sufficient statistics, so the parameters here are mu over sigma squared, that's one parameter, and the other one is minus 1 over 2 sigma squared. By the way, if you don't put the 2 or if you don't put the minus sign, doesn't matter, you know, things will work out, okay? But this is, you notice the eta transpose u, right, should give me this function and that function, okay? This is constant. So h of x, the constant term is 1 over square root of 2 pi. And then g of eta is whatever is left, that's a function of these parameters. And you have a sigma squared here, and you have these two terms there, this term. And you can show, it doesn't take any algebra, you can show basically that the coefficient on the front, the normalization factor, you can see it, this is minus 2 eta 2, so this times minus 2, you get 1 over sigma squared, there it is, and square root. Can you see that? That sigma square, right, is this term here, and exponential of this is this exponential. And the partition function, it looks like this, okay? So again, what we have learned, this is what we call the moment parameterization, right? We give the mean and the variance. What you have here is the canonical parameterization in terms of this canonical parameter theta. It looks more complicated, but maybe, right? This family of distributions may allow us to do things that somehow will be missing because we won't be able to generalize. And I'm going to try to show you, timing allowing, an example that is several, maybe 3 or 4 or 5 lectures ahead of us, but I'm going to show it to you now if I have time, just to get a sense on some magic you can do when you work with the exponential family.
Wait, what
Yeah.
is eta 1 and eta 2?
Eta is a vector, right? So eta 1 is mu over sigma squared, and eta 2 is minus 1 over 2 sigma squared. Okay? And you notice u is a vector also because it has 2 components, x and x squared. Okay? I put the transpose, this I write them as column vectors. Okay? All right. Now, the place where these exponential family distributions are being used, right, and hopefully you can connect this with the previous lecture, is they're used basically as priors, as conjugate priors, that somehow when you multiply them with the likelihood, they give you a posterior that is also in the exponential family. So it's like you assume a prior, let's say for the mean of a Gaussian to be a Gaussian, then the posterior comes to be a Gaussian with updated parameters. So effectively, the only thing you need to do is, if you start with a prior that looks like that, the only thing you have to do when you multiply this with the likelihood and you get the posterior, the only thing you have to do is update these functions, h of x, you know, a of eta, and eta, etc., to account for the data that you have collected. So let me give you an example of this general form of these priors, okay, that we have. Practically everything we discuss in the lecture on Tuesday and Thursday fits in this form. So let's say that we have a likelihood that looks like something coming out of the exponential family. All right, so this is basically our standard likelihood, okay? So we collect data and given some parameters theta, this is the likelihood. Okay? So it can be any data coming from any sort of distribution that we have discussed up to now. Okay? So what we do is we define a conjugate prior, and I remind you, conjugate prior will be a prior that if we multiply with this, we will get a posterior that has the same form as the prior. Okay? So here is a conjugate prior. You look at this, all right, and you say, look at this. So h of x we don't really care, so we need to define, this is a prior on theta, right? This is what we try to estimate. These are the unknown parameters. So here I have g of theta. So how about if I have g of theta to some power, that would be a parameter of the prior, and then I have exponential of eta transpose u. How about if I have eta transpose tau 0? Okay, and tau 0 is another parameter of this prior. A lot of times, and you will see the reason, you like to write tau 0 as mu 0 times tau 0 bar, right? Because we're going to try sort of to mimic some structure that exists in the likelihood. You will see this shortly, right? But effectively, the only thing we do is, we may want to rewrite this as another variable, mu 0 times tau 0 bar. Okay, nothing new. So multiply this with that, and let's see what we get. We get g. All right. So let's say there's actually no multiplication yet. This is still the prior. All right. So this is how the prior looks. I'm rewriting this equation. Okay. Nothing fancy. I just put also the normalization factor here. Here it was proportional, so I put the normalization factor of this prior, and I remind you the normalization factor. For the exponential family I gave it to you before, is basically, anyways, it's going to be the integral of what you see in the numerator. So when I integrate this, I get 1. So the prior is g to the power mu 0, exponential of eta transpose times tau 0, and sometimes we write the tau 0, mu 0, tau 0 bar. So let's see this in action. So we collect n data points. We collect n data points from the likelihood. So this is the likelihood of all my data points. So this is capital of X that involves x1, x2, xn. So effectively, with IID data, my likelihood is the product over n of all of these terms. We agree? You remember we said that the likelihood is of this form. So for every data point, I'm going to have this times the next data point, the next. So what I get is the product of all of this. So I have the product of this h is calculated at xn. And then I have g of theta. So this will be actually n of those. So it will be g to the power capital N. Okay? And then I'm going to have exponential of theta transpose. And the product will become a summation over all the u's. Okay? So this thing immediately you can appreciate will be the sufficient statistics that I need for the estimation of the parameters theta. So all the data basically collapse on that summation of the u's, and that's the only thing that you need to be able to estimate theta. So what I'm doing is now I'm taking the prior that I had before. So again, I wrote it in this form here, okay? This is the same thing. So let me multiply them. So when you multiply them, I don't put the constant term there. I have g to the power capital N plus a power mu 0. And then I have exponential of eta transpose. I have this summation. And then from this I have tau 0. And I said that I'm going to write tau 0, mu 0, tau 0 bar. Now you may say, you didn't explain to us why we wrote the tau 0 as mu 0, tau 0 bar. Here is a motivation for that. The summation of u, I can write it as n times the empirical value of u. So you can see immediately n0 serves as the fake prior data, right? Fake prior data with what value of this data? That value is tau 0 bar. So I basically try to mimic this n u bar, and I make this n some other u bar, which comes from the prior, that I call it tau 0 bar. And I think I mentioned to you this concept of pseudo data. It's only coming in the exponential family of distributions. Don't do that in any other distribution. But in the exponential family of distributions, you can put this meaning of prior data basically to explain the parameters in the prior model. So now, if you look at this distribution, what type of distribution is this, based on our lecture today? It's an exponential, and there it is, all right? And effectively, the exponential distribution, this is conjugate, is the same thing as the prior. The only thing is the parameters of the prior, like nu 0, has now become nu 0 plus the capital N. Okay, you can see from here, right? And that tau 0 bar has become now tau bar N, which is this. So it has my, this is where my data come, and this is my prior data, okay, divided by the total number of data counts. And if you want, you can write tau N equal this times that, and basically you get this this simple form. So the idea here is, right, simple. If somehow you use the exponential family and in this setup, effectively you take advantage of this conjugate relation, and your posterior comes to be exactly in the same family as the prior, so the calculations are effectively nothing else but updating the parameters of the prior. So very simple, okay, very convenient. Again, I put this normalization factor here, right, just to be sure that this distribution is normalized, and we may make use of this actually later today in the lecture. All right, so actually later in the lecture, I'm going to make use of it now, and I'm going to do a calculation that is sort of an advanced calculation, since we're Bayesian by now. So let's do an advanced calculation where we do predictions. All right, so in one slide, basically, right, we put the likelihood, the prior, the posterior. Now you say, I don't really care about the parameters. Let's say that I collected all this data, capital X, and you are asking me to compute the probability of future data given X. Right? That's the predictive distribution. There's no theta there. Because you remember I told you that theta is sort of, the parameters are an intermediate quantity. You don't really care. They just facilitate the process, but parameters have to be integrated out. Do you remember the formula for the predictive distribution? How do you get the predictive distribution? It was an integral of?
The f of x prime given the parameters.
So in this case, that will be an integral over the parameter space of the likelihood of x prime times the posterior of the parameters. The likelihood of x prime times the posterior of the parameters. So you know what I'm doing? It's like, all right, this is the likelihood times the posterior that we calculate. So the likelihood, you remember our likelihood has the same form as before, is the product of these h's times g to n prime, because I'm looking for n prime data, times exponential, not u of capital X, u of capital X prime, because this is the statistics of my future data, okay? And then I have the posterior, and the posterior, remember, is z calculated at the updated parameters, and the updated parameters for the posterior is nu 0 plus capital N, and u plus tau 0, okay? And then I had g to the power nu n, and then eta transpose to u plus tau 0, okay? This is basically this equation here. So effectively, we need to integrate this in the parameters theta. See now how the theta, you can have thousands of parameters, but I'm going to be able to do the integration exactly, because it's everything in the exponential family. The results look very nice. So let's see. This comes outside. There's no parameters there. This normalization factor comes outside. And then I have g to a power of n prime plus nu n exponential of eta transpose of u at x prime plus u of x plus tau 0. And I want you, don't look at this formula here, the blue. Look at this integral and tells me if it looks familiar to you. What is that integral? What does it remind you? Huh? What does this, actually forget the integral. What does g to some power times exponential of eta transpose times this reminds you? Part of the exponential distribution, what is missing? You know what is missing? The normalization factor. So what is this integral? Is the normalization factor of an exponential distribution with this parameter and this sufficient statistics. And there is that z here, and there is the predictive distribution in a closed form. Okay? How would you like to be able to compute the predictive distribution for this whole family of things, everything, right, in one formula? And you say, is this it? The answer is yes. And you remember I was telling you why the normalization factors of these distributions are essential. You can see here, to be able to compute this predictive distribution, you need to know z. And of course, for the exponential family, we know z. It's a complicated expression, but we know it. Okay? So in this case also, I'm noting here, if your previous data is equal to 0, effectively what you get here is you get the marginal distribution of x prime. This is what I call on the lecture on yesterday, I call it the model evidence. Okay, it's the evidence of the data. So if you don't have any previous data and you're asking the probability of x prime, this quantity basically will give you the probability that you will observe data x prime without any prior observations, okay? All right, so we did the posterior predictive, nice. Okay, I have another example where effectively I'm applying, so we did this in general, all right, for any distribution. So I am not going to go through this example, but I want you to, when you go home, do this calculation, and the calculation is basically the following. This is what this slide is about. The likelihood is a Bernoulli distribution. So I do, heads, tail type of experiments. I throw the coin n times. So this is my likelihood. I put a prior that is a beta distribution, right? This is what we did earlier, I think on Tuesday. You make it to look like, to fit in the exponential family, both ways, both the likelihood and the prior. And you can compute in directly with no answers, basically no derivations, the posterior. And then you can pose the nice prediction problem and say, look, if in n previous trials I predicted, I came up with m heads, what is the probability that if I do m prime new experiments that I will see s prime heads? So if you want to go to the casino and you want to play your luck, this is type of a calculation. You say, I know before I got 3 times heads and everything else, tails, what's the probability now that in 10 experiments that I will get, let's say, 5 heads, okay? And so effectively it's an application of the previous formula, and you can see the answer comes in terms of these normalization constants of the beta distribution. Okay? These things will look, sorry for the expression, they will look Chinese unless you actually work with them. Okay? I mean, Greeks, Chinese say, this will look Greek to you. To me, I say they look Chinese, okay? So, what I suggest is if you look at the general slide, you really appreciate that it's sort of straightforward algebra, okay? And as straightforward as it is, right, simple things lead to very complicated looking things. And this is what we have. But the result, I hope you can appreciate, that has a significance. It's not, we're not talking about a coin tossing problem. It's significant. You try to do future predictions, you try to use previous data. This formula, if you play with the exponential family, it tells you what is going to happen. Okay? Not trivial. All right, so let's keep going. So you may ask, are any fundamental unifying properties that these exponential families have? I mean, we did some derivations now, for the posterior, the predictions and all of this. Is there anything else? The answer is yes. Okay, lots of good things. So, let me start with the following. This exponential family distributions, obviously the way we set them, they are normalized. So you agree with me that this integral is equal to 1. Okay? So let me do the following magic. I am going to take derivative of this equation with respect to the parameter theta. Okay? And, let's see what's going to happen. Okay? So I'm going to take derivatives of this normalization equation with respect to the parameter theta. You agree that there is theta here and there is theta there. So this term will give me gradient of g, and I can put it outside the integral because it doesn't depend on x. H times exponential of eta transpose u dx, fine. And then I have g times h, and then I'm going to differentiate this with respect to eta. So I'm going to get the exponential of eta transpose u times u. Okay? So let me do the following now in this equation. Multiply the first term by g and divide by g. So g times, if I put it inside the integral, g times a is exponential of this dx. How much is equal to? 1. So basically what I have here is, I have gradient of g divided by g, and if I put it on the other side, I'm going to get a minus. And here what I have is g times h, exponential of eta transpose u. And you know what? What is again g times h times the exponential? What is g times h times the exponential? Is my distribution. So what is this whole integral? It is really the expectation of u of x. So here is an amazing result. If you, so here I have minus gradient of g over g. Let me simplify. You remember my partition function is 1 over g, the normalization factor. So really, A is the log of the normalization factor. By definition, this is how we define it, is minus the log of the g. So would you agree with me that if you take the gradient of A with respect to eta, you will get 1 over g times gradient of g? So really what this thing is gradient of A, okay, is equal to the expectation of the sufficient statistics. An amazing result. So it tells you basically, by taking derivatives of A, okay, one derivative here, you recover basically the expectation of u of x. Okay? And it doesn't finish actually there. Guess what will happen if I take a second derivative of A with respect to eta? So the derivation is given here, so this is the expression from the previous slide. If you take another derivative, you do the algebra, you recover the covariance of u of x. Applicable sort of to any distribution, not just Gaussian, but any distribution in the exponential family. And by the way, you see here another important result, because the covariance is greater than 0, right? Then you can see that the second derivative of A is positive, so A as a function of eta is convex, and that has significant implications on what I'm going to say shortly. Okay, A is a convex function. So I don't want to go through the details of this example because we will not manage to finish the lecture today. But effectively, what I have done is I went back to the previous slide that we discussed about the univariate Gaussian. Okay, and I took the definition of A to be minus log of g, so I wrote A explicitly, and then I start taking derivatives, and if you look at the algebra, there is nothing there. With first order derivatives, you can discover, if you take derivatives with respect to eta 1, you discover the mean of x. If you take derivatives with respect to eta 2, you discover e of x squared. If you take, like that, you discover the variance, and you keep going. Everything is coming basically for free. Now you may say, yeah, I mean, it's coming for free, but all of these results you're telling us, we knew them. Well, you know what? The Gaussian is a homework application. Try to think that things can be much more general than the Gaussian. So, so this is what we derive, right? So that the expectation of u, okay, the expectation of u is the gradient of A with respect to eta, and we already said that this is a convex function that looks like that. And you know what that means is if you look, so let's call this mu, okay? And I like to call mu, to put it in an analog with the mean, right? The moment, okay? Because really the expectation of u is a moment. So let's call it mu, okay? So this in the Gaussian can be in the mean, the variance, okay? So I call this mu, and so obviously you can see that mu is a function of eta. And because this function is convex, this function is increasing, okay? So you know what I can do actually? I can invert this relation and I can say immediately that there is, for every mu, there is a unique eta. And you know what that means? If you start with a moment parameterization, you can find a unique representation in the canonical way in terms of this natural parameter theta. And if you start with some natural parameter theta, there is a unique parameterization in terms of the moments. So it's not like you can do this or that, but you know it's not unique. No, according to this, if you give me eta, I can compute mu, and if you give me mu, I can invert this relation in principle and compute eta. Okay, so let me. So you remember when we worked, for example, for the Gaussian, all right? One of the results that we computed, I don't know if it was this Tuesday, we computed for the Gaussian that the MLE estimate for the mean is what value? So if you collect some data, what's the MLE estimate for the mean? For samples coming from the Gaussian. It was the empirical mean, the sum of the x's divided by n. So the question is there any chance actually that the same result is generalized for everything in the exponential family of distributions? Of course. So let's look. Take the likelihood to be in the exponential family, nothing fancy, all right? We like to work with the log likelihood to make the algebra easy, okay? And so the log likelihood looks like that, okay? N times the derivative of g, so it will give you minus a plus eta transpose u. And then what we want to do is we want to maximize the log likelihood. That's the MLE estimate. We want to find the MLE of the parameter theta. So when you take derivatives with respect to eta to find the MLE estimate, what you get here is n times the gradient of A, and what do you get here? Summation of the u's. So if you put the n on the other side, you get the empirical mean equal to the gradient of A, and what's the gradient of A? The exact expectation of u. So basically that result that we saw for the MLE estimate, it is true for any member of the exponential family. Very nice result. Okay? I mean, you just really, I mean, if you understand it in the general setting, you don't have to go and prove it for every distribution in the family. Immediately, this is sort of a wonderful result that tells you that this empirical mean is the actual mean of the distribution. Okay. Some point, we discussed briefly this. We introduced, when we talked about information theory, we discussed about entropy, and we discussed that there are distributions that maximize entropy. So I'm not going to go through this slide. You can read it, all right? But if you say you have, if you look for the distribution that maximizes the entropy, but satisfies some constraints. So for example, these constraints, you can interpret them, you say, I want the mean to be equal to this value, and I want the variance to be equal to that value. Can you tell me what is the distribution that satisfies those two constraints that maximizes the entropy? Now, if it is the mean and the variance, we know the answer is a Gaussian. But in general, if you have any set of constraints in the moment, so you're asking to maximize the entropy, the distribution comes to be in the exponential family. So maximum entropy distributions and exponential family, in the literature sometimes people interpret it one way or another, but it is the same thing at the end of the day. Okay, it's better for at least for our course to say that these maximum entropy distributions, they are members of the exponential family distributions, right? Rather than the other way around. All right, I have, how many minutes I have? 10? When do we supposed to finish today? 20? At 20, okay. All right, so I'm going to do something that is a little bit ahead of us. If you appreciate it, we're not going to do the same example again, all right? But this is the right time to do it. And it is a little bit complicated, but the result you get is amazing, okay? So that you don't say that the course is elementary. So suppose we have, we are doing what's called a regression problem. So you're trying to fit a function to data x and y. You have data x, so I give you some x values and y values, and you try to fit some function, okay? And the way usually you will fit that function, you will assume that somehow there is, for, if you look at any x, you will actually consider a model that is a distribution, and you say, I want to use that distribution with some mean value, and this is the mean value, and I'm going to make that mean value to be some function of x, all right, and some noise. Okay, so think, you're fitting something, right? You're fitting it, let's say, with a Gaussian, and this is the mean of the Gaussian. Okay, and I'm not gonna. I want your imagination here, right? So effectively, if you do fitting, you will only think of this function, and because we're talking about what's called generalized linear models, this function depends on the parameters in a linear way. So this function can be linear, but is a function of theta transpose x. The parameters come linearly there. Okay? So this, you can think is, this will be your mean function that you fit in, but obviously there is some noise around that function. So again, you give me data x and y, can be endpoints x and the corresponding endpoints y, and I'm going to try to fit the conditional distribution of y given x. This is really what we're looking, right? So if you give me x, you are asking me what's y. So the conditional distribution is going to have this mean, all right, where xi is theta transpose x. You're with me on the problem? We're fitting a function to data, okay? All right. So let me give you a schematic. So basically we have the parameters theta, we have x, so we define theta transpose x. Obviously x, I make it to be not one dimension, can be high dimensional, many variables, all right? And I told you that the mean of the conditional distribution is mu. Actually, this is a typo, so you put a Greek mu, all right? So through the function f, the xi gives me mu, okay? And now what I'm gonna do is, I am going to consider that this distribution comes from the exponential family. And if it comes from the exponential, you remember what I was telling you? That there is a unique parameterization from mu to eta to these canonical variables. And let's say the mapping from mu to eta is psi, which is for a given exponential family is written, it's known, okay? So again, theta and x takes us to x, to xi. The mean then is coming through this function f, and the mean can be mapped to eta through psi that's defined from the exponential family. Now, okay, you use an exponential family, and you may say, is there any convenient way, if I select an exponential family, is there any convenient way to select that mean function f to fit my data that somehow will make the calculation easy? So let's look at this picture. look at this. So my function, that this convenient function that I am going to use, is going to be psi minus 1. Let's see what that means. So xi through f goes to mu, okay? But also mu comes from eta by psi minus 1. Okay? So when I say, so basically to compute mu, I can either operate with f on xi, or I can operate with psi minus 1 on eta. And what I do here is, I'm going to take xi and eta to be one and the same. I'm going to take xi and eta to be one and the same, because, you know, if these two functions are the same, and one maps xi to mu, the other one maps eta to mu, I better have xi and eta to be the same. All right? So this choice of the function f is called the canonical response function. All right? So again, basically our choice says, you know what? This regression function, make it to be psi minus 1 and make xi and eta to be one and the same. So let me see if the next slide, actually the next slide summarizes lots of the things we discussed about the exponential family. So let me see how we're going to learn about regression before we have said anything about regression. Okay? So somebody gives you data x, and let's say the function we fit is scalar. So y is scalar, x can be a vector, so and you give me n data points. So the likelihood is on the exponential family, so I use the classical form. The only thing that is, you remember here, we're looking for the conditional distribution, all right? So my sufficient statistics for each data point, when I do a regression point, and I look, let's say, condition on x, I'm really interested in the value of y. So the sufficient statistics u that we had before is the yn value. Right? That's the only information I have. So the u here is yn. The rest is exactly the same as before. These are the natural parameters theta. Okay? So for this selection of the function f, the canonical response that I mentioned before, we take eta to be the same as xi, and xi is theta transpose x. So if I go here and I put as theta transpose x, all right, then my likelihood looks like this. Okay? And notice, by the way, how nicely you get sufficient statistics basically to compute the parameters that involve the product of the x vectors with the corresponding y's. This, by the way, it is fundamental to many algorithms, machine learning, where you get x times y. Okay? So again, what I have done is, for our choice, this is equal to xi equal to theta transpose x, and you get something like that. All right, and let's not be Bayesian or anything like that. Somebody will say, if this is the likelihood, can you compute, take the gradient of this with respect to theta, and tell me how to compute the parameters theta, because this is what we're interested in. So if you take the gradient of this with respect to the, actually, so we're going to take the derivatives with respect to eta. And actually, let me look on this formula, because it will make a little bit more sense. So on this term, you have a gradient of a prime is the gradient of a times the derivative of theta with respect to theta. Okay? The derivative of theta with respect to the parameters theta. Okay? On this thing here, what you get is, you get y times the derivative of theta with respect to theta. Okay, so if you, what is the gradient of A? You know what's the gradient of A for the exponential family? Is the mean. All right, so this for each point, xn, you look at the conditional distribution, that is the mean. So what you get is, you get sort of the error, because this is the mean, this is the measured value, right? So this is the error, okay, times the gradient of theta with respect to theta, and if you look here, the gradient of theta with respect to theta is really xn. So effectively, the gradient of the log likelihood, what it is summation of yn minus the mean times xn. And if I put all of this in a matrix form, is if you put all the data together, is a matrix X transpose times Y minus mu. Okay? So, how do you compute the parameters now, theta? Okay? So, we're almost, I have to run, and we will do this once, we'll repeat this on next week. So, this is the gradient, X transpose Y minus mu. You can actually compute the second derivative, which is the Hessian, and you can direct it from there. It comes to be X transpose Wx, where W is these derivatives that you see here, that you can compute for the exponential family. And what you can do is to compute these parameters theta, you do iterations using the Newton algorithm. Okay? If you click there, it will take you to Wikipedia, and on the first slide, you will see what the Newton algorithm is, if you have not seen it. Let me tell you what the answer comes to be. It comes to be weighted least squares, basically. And this algorithm that is going with the name iterative reweighted least squares method, it's sort of universal in this sort of problems with the exponential family and computing unknown parameters, okay? It's iterative reweighted least squares method, and it comes out, if you apply this method point-wise, you actually get an algorithm that it is practically identical to stochastic deepest descent that people use in training neural networks, and in exactly the same form. So look at the last 3 slides, and I'm going to come back and remind you basically on the details. So I think we have done enough work on in the lectures, so you can operate in the homework. So as of today, the homework is due on whatever date says it is due. If you have any questions, please forward them to the TAs, and if you don't get a response, forward them to me. Okay? So I will see you.